And both of these fall into what we call phospholipids. They are found chiefly in animal tissues. Those that have glycerol as the backbone, and those that contain sphingosine as the backbone. Just like how waxes didn't have glycerol as the backbone, but in this case, sphingolipids don't have glycerol as the backbone, they have a molecule known as sphingosine. Now both of these classes of molecules are found as structural components of membranes, and both play a very important role in the generation of lipid signaling molecules. In some plant tissues, sulfur or galactose are used in the place of phosphates. Instead of phospholipids, you would have sulfolipids and galactolipids. It is posited that the reason for this is the limiting amount of phosphate that may be in the soil, but we don't have any proof of that. Just remember that in plants, instead of phospholipids, a lot of time you would find sulfolipids and galactolipids, especially in the membranes of the chloroplasts and so on. Now, glycerophospholipids, also known as phosphoglycerides. Right, these are derivatives of phosphatidic acid, and here we have a phosphatidic acid. So here we have the glycerol backbone. Attached to it are the 1 fatty acid, 2 fatty acids, but unlike triacylglycerides, where the third fatty acid should be, we have a phosphate group to which some substituent may be attached. Now if this X, this substituent, is a hydrogen, that is phosphatidic acid. And now I'm glad I wrote in this point. It's important that we realize that carbons 1 and 3 of glycerol are not identical. So here we see carbon 3, that is where you would usually find the phosphate group attached. For carbon 1, that's a fatty acid chain. The carbon 3, not carbon 1, is where you would have this phosphate group attached. And as I just stated, when the X is hydrogen, it is known as phosphatidic acid. Okay, now we have a table here showing what the X could be and what the compounds would then result. That would be. Okay, if the X is H, as I said 2 times, then it would be known as phosphatidic acid. If the X is this ethanolamine molecule, it is known as phosphatidylethanolalamine. So if you had an ethanolamine molecule here, this would be phosphatidylethanolalamine. If you had choline, now this is very important, if you had choline there, it would be known as phosphatidylcholine, which is also known as lecithin. We'll speak about that a little bit now, just now. So if you had a choline attached to it, it would be known as lecithin or phosphatidylcholine. If you had serine attached, it would be phosphatidylserine, glycerol, blah 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 blah. You have cardolipin, yada yada yada, same thing. Now I want you to look at the top here. We see that both phosphatidylethanolamine and phosphatidylcholine have a net charge of 0 at physiological pH, and because of this, these molecules can easily pack into membranes. You see that it's written at the bottom here, yes. Okay. Now here we have a diagrammatic representation of what a phospholipid bilayer would look like. Now if you just were to maximize one of these phospholipids, you see, you have majority one head and the 2 tails. Well, the tails in fact are the fatty acids and carbons 1 and 2. The head is the phospho part, where the phosphate is attached to the substituent. In this case, the substituent is a serine molecule, so we have phosphatidylserine. And here we have another example. So just remember that the head is the phospho part, and the tails are the fatty acids and carbons 1 and 2. This diagram came from one of the textbooks. I'm sorry, I can't remember which, but as I advise you, read the textbooks. Okay, we just spoke about this lecithin, also known as phosphatidylcholine, or I should say phosphatidylcholine, also known as lecithin. This has a choline molecule attached to the phosphate group on carbon 3. Now, lecithin is found in the brain and in the egg yolk. In fact, I think the word lecithin comes from something related to egg yolk. I can't remember the exact thing right now. Lecithin is important in fat metabolism and transport and is an emulsifying agent in the food industry. Though this video isn't focusing on fat metabolism and transport, when you're doing HDLs, high density lipoproteins, you would come across a molecule named LCAT, which stands for lecithin cholesterol acyl transferase. Now this is an enzyme, a transferase, lecithin cholesterol acyl transferase. The reason it's so named is because it transfers one of these acyl groups, one of these acid groups, from this lecithin molecule to cholesterol. I remember we mentioned previously that when an acid and an alcohol react, you have an ester forming. So when an acyl group reacts with that cholesterol, you have a cholesterol ester forming. So next time you see that LCAT leads to the formation of cholesterol ester, just remember I told you so. Okay, dipalmitoyl lecithin. This basically means that the two fatty acids attached are palmitic acid residues. These play a very important role as a long surfactant. Now this is very important. Lung surfactants prevent the adherence of the lungs' inner surfaces, and without this, respiratory distress syndrome would occur. And this, so sometimes when you have premature babies being born, if the surfactant isn't fully developed, this may cause respiratory distress. And what happens is, by reducing the surface tension, it aids in the reduction of the pressure needed to reinflate alveoli, and this prevents atelectasis, which is alveolar collapse. This causes it. I think one description given to this is that it's easy to open a door that is ajar and one that is closed. So if this surfactant isn't there, the door is basically closed and it's very hard to reinflate. Now cephalin. Once again, you have two fatty acid chains and this molecule attached here. And here we see that this molecule could either be phosphatidylserine or phosphatidylethanolamine. Now anytime you see something with the prefix ceph relates to the head. So cephalin is found mainly in the white matter of the brain, nerves, neural tissue, and the spinal cord. Now, whereas lecithin is the principal phospholipid in animals, cephalin is the principal one in bacteria. Whoa, this is very long. Phosphatidylinositol aids in signal transmission across membranes, and it plays a role in membrane protein anchoring. So once again, we have this is our glycerol, carbon 1, 2, 3, phosphate, and that group attached. Diphosphatidyl cardiolipin. Now what I drew here is not the entire molecule, just the X portion. And if you notice here, you would see a glycerol backbone, two fatty acids and a phosphate group. Another glycerol backbone, away from somewhere in the phosphate group. Now these two join together form the X. It's like if you have three glycerols on one thing. But the reason we call it diphosphatidylglycerol is because if you have two phospholipic acids at the X portion. This is basically saying the same thing. They are found in the inner mitochondrial membrane, and that's what I was just explaining. It is found in bacteria and eukaryotes. In eukaryotes, cardiolipin is virtually exclusive to the inner mitochondrial membrane, where it appears to be required for the maintenance of certain respiratory complexes. Note well, this does not only relate to cardiolipin, but to all the phospholipids. The fatty acids may vary, and hence a number of phospholipids may form. So while we were speaking about the X portion all the time, the fatty acids on carbons 1 and 2 may not be the same thing, and as a result of that, we have to have a variety of phospholipids, glycerophospholipids. Now, some phospholipids, instead of having an ester linkage, they have an ether linkage, which we spoke about earlier, on one of their fatty acids. If these chains are saturated, they are known as acyl ether lipids. If there is a double bond between carbon 1, see carbon 1, and carbon 2 of the fatty acid, they are known as plasmalogens. See here we have two fatty acid chains and a phospho part. But if there is an ether linkage between carbon 1 and carbon 2 in this chain here, you're known as plasmalogens. The head group of plasmalogens are usually choline or ethanolamine, and they make up approximately half of the heart's phospholipids. Within the heart you have phosphatidylcholine. Now this is not phosphatidylcholine. It's similar, but in phosphatidylcholine this was an ester linkage. In phosphatidylcholine it's an ether linkage. And in nerves you have phosphatidylethanolamine. Now another category of plasmalogens is platelet activating factor, and this ether lipid is secreted by basophils. Some of the functions include stimulating platelet aggregation, members named platelet activating factor, and the release of serotonin, which is a vasoconstrictor from platelets. So this has similar functions to thromboxanes, I believe. And they also mediate hypersensitivity, acute inflammatory and anaphylactic reactions. But this has functions similar to natural prostaglandins, I believe, but I have to check them out. Classifications of lipids. So we've done fatty acids, we've done eicosanoids, triglycerides, waxes, glycerophospholipids,